Hello, students, and welcome back to our next lesson in light. Yesterday, if you remember, we were talking about reflection, and we discussed the different types of mirrors. I wonder how many of you can remember the 3 types of mirrors we discussed yesterday. Well, today we're going to take this topic of light a step further, and we're going to transition from yesterday's reflection to today's refraction. So we're going to be talking about refraction this period and a couple of tools that are used to refract light. So before we get into refraction, I want to give you an analogy here to think about. How many of you love summertime? How many of you love to swim? How many of you love to swim in a pool? And how many of you know what a belly flop is? How many of you have ever belly flopped yourself? Okay, you know how painful it is then when you jump into the water on your belly and you belly flop and it hurts. My question to you is, why? Why does it hurt when you belly flop? Well, you might be thinking to yourself, well, duh, you're landing flat on the water and it hurts. I want you to think about belly flopping here just a little bit longer. If we look at this picture here, we see this dude who is obviously jumping off of a diving board here and is ready to belly flop in the pool. And if you've experienced this before, you know that this dude's belly is going to turn red soon because it's going to hurt. But why? Well, through the air, the velocity or the speed at which this person is falling is at a certain rate. He's falling through the air, which has a certain density, and it enables him to fall through that air at a certain speed. In fact, it's the rate of gravity. But here's the deal. Water does not have the same density as the air above it, right? Water is a lot more dense. It's got a lot more mass in the same volume, and so its density is greater. And so when an individual or an object of any kind falls through air and then hits the water, what happens to the speed of that individual? They're going to slow down very quickly. Very quickly. Now, not as quickly as if he would have belly flopped onto concrete, because that would make his velocity stop altogether, and it would make his brain and heart stop altogether as well. So we don't even want to think about that. But if you belly flop into the water, your velocity is changing as you go from air to a liquid, to the water. You slow down because of density. Well, why are we talking about belly flopping? Well, I think it's a pretty good analogy for what happens to light when light experiences refraction. Refraction is what happens when light bends due to a change in speed when passing between different types of material. So think about light entering into this pool for a moment. Light is traveling at a certain velocity, the speed of light, as it's shining through the air in those parallel rays we talked about yesterday. But as soon as that light hits the water, which is also transparent or see-through, it has a different density and its light speed changes down. it slows down. And when it slows down, just like this belly flopper changes speed, so does light. And as that light slows down, it actually changes the angle that we see it. We call that refraction. And later in the lab we'll actually do this demonstration. Imagine a glass of water. I think we saw a video of it yesterday. A glass of water, and you put a pencil into it. It looks like the pencil is bent. That is because of refraction, the refraction of light. If you were a person who wanted to go spearfishing, let's say, and there was a fishy swimming around in the water, and you wanted to spear that fish as you were above the water, you don't want to aim where you see the fish. What? Yeah. If you aim where you see the fish, you're going to miss every time. Because of refraction, the fish is in a different position than what it looks like from above the water. So you have to aim in a different position in order to spear that fish. Otherwise, you're going to miss. So refraction is, again, that bending of light due to a change in the speed of that light when passing between different types of material that have different densities. So this dude, when he hits the water, he slows down markedly because of the different density of water. All right, maybe that's a bad analogy, but hopefully you get the idea that the refraction of light involves the bending of light. You're strong enough to bend a beam of light simply by passing it through a different material. Now, there's a cool little device here. I have one here. This is called a prism. And in the class, I'm going to show you a light beam traveling through this prism. And because the prism is shaped like a triangle, thinner on one side, thicker on the other, a prism enables a light beam to be spread out, to be bent or refracted into the different colors of the rainbow. Think about last week when we learned about the electromagnetic spectrum and electromagnetic waves and how different colors of light have different wavelengths. And those wavelengths, as they enter a prism, will be refracted at different angles because of the different wavelengths. And that's what enables us to use a triangular prism like this one, and again, I'll show it to you in the lab, and how it spreads light out according to the colors of the rainbow, Roy G. Biv. And this is how Isaac Newton performed his famous light experiments many years ago and discovered the colors of the rainbow from a single beam of white light. But prisms are not the only cool tool that we will be using in the laboratory. In fact, tomorrow we are going to be creating a telescope, and more on that in a few moments. But the tool we will use to make our own homemade telescope in the lab are lenses. So what are lenses? You see a variety of examples here, from contact lenses to glasses. Glasses are a type of lens, to camera lenses, to hand lenses, which we're going to be playing around with a lot tomorrow, to, I'm not even sure what this is, some type of a cool lens that is held in the hand. Actually, that looks like, it almost looks like a one of those crystal balls, which also is a type of lens, believe it or not. But all lenses are transparent, meaning water can shine through them, and a transparent material that actually refracts light. So a single flat window pane, and we mentioned window glass yesterday, allows light to travel through it, doesn't refract light. What you see through a window doesn't appear any different than what it actually appears like on the outside of the window, because there's no refraction of light. A lens has to be curved in a certain way in order to refract light. So we're going to talk about two types of lenses, and I'm going to demonstrate for you the cross sections of these two types of lenses. One is a converging lens and one is a diverging lens, but we are going to attach different names to them. We're going to call them a convex lens first. The first one is a convex lens. And a convex lens is one that is thicker in the middle, like me. And it refracts light to a point. These are the most common types of lenses. Convex lenses. Here I have a couple of examples of convex lenses, and we're going to have a lot of fun with convex lenses. Convex lenses, also known as hand lenses or magnifying lenses. These lenses are thicker in the middle, which enables them to refract light towards the center, to a place called the focal point. So as you're copying these lines in your book, pay attention to the fact that these lines that are parallel to one another are rays of light coming from a light source. And as the light enters the lens, and I want you to keep in mind this is a cross section of a lens. So if we're looking at a lens like this, and if we were to cut it right down the middle and then look at the cross section of a convex lens looks like this. Okay? So as light enters into a convex lens, light is always refracted to the thicker point, which in this case is the middle, which enables light to be bent or refracted to a single point called the focal point. So this is an example of a convex lens. And one of the things we will be doing in the laboratory with different convex lenses is measuring the distance between the lens and that focal point. And I'll show you how we're going to do that using light. That distance is called the focal length. So be sure to copy this in your notes. The focal length is the distance between the lens and the focal point. And that information is going to be really important for us on lab day when we compete against one another to make the most powerful telescope in the class. You will definitely need to be able to measure the focal length to win the competition on lab day. So a convex lens is one type of lens. The other type of lens is a concave lens. A concave lens is one that is thinner in the middle. And let me show you a cross section of a concave lens, and here's a real example of a concave lens. Again, remember, if this were a concave lens and we sliced it down the middle and turned it to the side, this is the cross section that you're drawing in your diagram. A cross section of a concave lens is thinner in the middle and thicker on the sides, which is why As light enters a concave lens, the light is always refracted to the thicker portion of a lens. So in the case of a concave lens, the light is refracted outward because that's where the thicker part of the lens is. So light is refracted outward, which means there's no focal point with a concave lens. It spreads light outward, it bends light outward, it refracts light outward, always to the thicker side of the lens. Now, concave lenses have their uses as well. Both convex and concave lenses are lenses that can be used in optical instruments like microscopes and telescopes and even eyeglasses, depending upon whether you are farsighted or nearsighted, will determine what type of lenses an eye doctor might use. But now let's put this knowledge into practice a little bit and talk about telescopes. After all, this unit we are studying astronomy, and in our study of astronomy, we want to look at objects that are really far, far away, and an instrument used to view an object far away is called a telescope. Tele prefix means far away. Scope means an instrument used to look at something. A microscope, an instrument used to see small things. Telescope, an instrument used to view faraway things. So back to telescopes. Galileo, we've learned about Galileo in the past. Galileo. Galileo was a famous scientist who is credited with using one of the earliest forms of a telescope to make some outrageous observations. In fact, when we get to the solar system, we're going to talk more about Galileo's observations of the outer planets. So more about Galileo later on. But let's talk about telescopes right now. Not all telescopes are the same. By the way, how many of you have a telescope at home? Okay. If you've got an inexpensive telescope at home, you probably have one of the two types of telescopes. I'll actually be showing you both types of telescopes in the lab tomorrow. We have a number of telescopes here at the school that we're going to be using, but there are two general types of telescopes that you need to be aware of. Now, there are different kinds other than these, but these are the two general types of telescopes. And if we just look at these diagrams here for a moment, the one on the right uses a lens in order to focus light to the eyeball, and the other telescope uses a mirror in order to focus light to the eyeball. So this is a picture of these two types of telescopes. How many of you have a telescope that looks something like this at home? This is called a refracting telescope. How many of you have a telescope that looks like this at home? This is called a reflecting telescope. So let's explore these two types of telescopes in a little bit more detail right now, beginning with the type that we are going to be making tomorrow in the lab. A refracting telescope. A refracting, think of the word refracting. Refracting bends light, or is the bending of light. And in order to refract something, we use a series of lenses because lenses refract light. So a refracting telescope uses lenses in order to collect light from a distant location. Now, I'll give you some time here to copy this illustration of a typical refracting telescope. So you can be drawing this while I am explaining the drawing to you. So here we have a telescope, and we're going to assume that it is pointing to the right of the screen here, and the light source may be coming from a distant star or planet. And as that light enters the telescope, it is first being collected and focused by a larger lens called the objective lens. The objective lens is the lens closer to the object that we are examining. Now, as the light enters that objective lens, it is bent or refracted to a focal point. And again, we could measure the distance between the lens and the focal point, and that would be called the focal length. We'll need to know that for tomorrow. Now, once it reaches a focal point, it may be way too small for us to see with the unaided eye. So we use another lens called the eyepiece lens. And because all of our eyeballs are different, our eyepiece lens is adjustable. It can move back and forth in order for our eyeball to be able to see the object, whether it's a star, planet, or satellite, other object in the sky, in order for us to see it with our own eye. And speaking of our very own eye, here's the model of our very own eyeball. In our very own eyeball, we have a lens inside our eyeball that enables us to focus and fine-tune things even more than an eyepiece lens. So as light enters the pupil of our eye, we have muscles in our eye that squeeze, contract, or expand a flexible lens that's behind our pupil and in front of the retina in the back of our eyeball. And our eye's lens is like a secondary eyepiece lens because it's our eyeball lens. And it fine tunes that lens, which really focuses an image so that our brain can interpret that light in a picture view. And so refracting telescope uses lenses to collect light from a distant object. So that's the basic structure of that's all, folks. That's the basic structure of a refracting telescope, and we will be using lenses tomorrow in order to produce a refracting telescope. All right, let's get to the second type of telescope here, which is called a reflecting telescope. Now, if a refracting telescope uses lenses to collect light, what do you think a reflecting telescope might use to collect light? Say it out loud if you think you know. That's right, mirrors. A reflecting telescope uses mirrors to collect light from a distant object. So I'll give you a moment to copy this diagram down, but here we have a body tube and a concave mirror like the one we were playing around with yesterday. This concave mirror, which enables you to magnify things because it's curved inward and allows light to reflect to a focal point. That concave mirror is what is used to collect light and focus it to a point. And then a plane mirror, a flat mirror, and you remember talking about the plane mirror from yesterday. The plane mirror then reflects that image up to an eyepiece lens that you can then use in order to focus the image to your eyes. So, in a nutshell, there is our two types of telescopes, reflecting and refracting telescopes that uses either lenses or mirrors to collect light from a distant object and focus those objects so that we can see them at a distance. So tomorrow we will continue with some more information and explore the details of our lab activity for tomorrow when we make our own refracting telescope. So until then, I'll say bye-bye.